Hello everyone, this is Uday and welcome to Uday Lectures. In this video, we will try and understand insertion operation and search operation in binary search tree. So without any further delay, let us get started. First, we will discuss about insertion operation in binary search tree. So to insert a new element into binary search tree, there is one simple rule is that we cannot replace any existing nodes in the binary search tree with the new element or with the new value. So we can insert a new value only as a child node per leaf node in the binary search tree. That means I cannot insert a new value in the existing nodes of the binary search tree. We will see what different steps we follow for inserting a new value into binary search tree now. So the steps are very simple. So first we will start comparing the new element value with the root node, and if the new element value is smaller than the root node, then we will try and insert the new value as left child of root node if the root node is not having any left childs presently. If in case the root node is having a left child, so we cannot insert our new value as left child. So what we do, we start making comparisons with the left child of root node. And again, if the new value is smaller than the left child of root node, then again we will see if the left child of root node is having any left child again. So if it is not having any left child, then we can go ahead and insert new value in that particular position. Always remember, a new value can always be inserted only as a child node for the leaf node or only in the null position. And in case if the new value is bigger than the root node, then we will try and see if root node is having any right child. If it is not having any right child, we can insert new value as right child of root node. And if in case if it has any right child, then we make comparisons with the right child of root node with our new value which to be inserted into the binary search tree. And again, if the value is smaller than the right child of root node, we will try and see if the right child is having a left child. If not, if it is bigger, then we will see if it is having any right child or not. And we can insert a new value only at the null position. So this is one simple rule which must be followed. So let me just give you a small example to understand this. So let us say I have the present binary search tree like this, right? And if I have to insert a value called 5 in this case, what I have to do is I have to start making comparisons with the root node. So the root node value is 10. So I am comparing 5 with 10. So we know that 5 is smaller than 10. So I have to insert this 5 as left child of 10. But before inserting, I have to make sure 10 is not having any left child. So here there is no any left child. So I can replace this null position with 5. If I have to insert value 3 now, I have to start making comparisons again from the root node, which is 10. So again, 3 is smaller than 10. So I can insert 3 as left child. But however, left child of 10 is 5 and it is not null. So what we do, we make comparison with left child of root node. So what is the left child of root node? 5. So now the comparisons are between 3 and 5. So we know that 3 is smaller than 5. So I can insert 3 as left child of 5. And since 5 is not having any left child, I can go ahead and replace that null value with the new element 5. And it happens similar with the right childs also. For example, if I have to insert 20, I have to start making comparisons with 10. And we know that 20 is bigger than 10. I can insert this as right child. And since 10 is not having any right child, I can replace that null position with our new value, which is 20. And if I take one more value, let us say 15 this time. So the comparisons will start from the root node, which is 10. And we know that 15 is greater than 10. So what we do, we have to insert 15 in the right child position. But 10 is already having a 20 as right child. So we have to make comparisons again with 20. So we will compare 15 with 20. We know that 15 is smaller than 20. Now 15 has to be inserted as left child of 20. And the 20 is not having any left child. So I can go ahead and replace that null position with 15. So this is how the insertion operation works, and the steps are followed. So these steps must be recursively followed, And one other rule or a simple step that I forgot to mention across here is that if the binary search tree, if BST is empty, that means there are no any nodes in the binary search tree or in the starting position of the binary search tree. In that case, I can make new value as my root node. So for example, if we are asking to insert 40, where this is the first element in the binary search tree, then we can make 40 as root node directly. We don't have to make any comparisons. So this is what this particular step mean. Hope you understood this. Now let us dive into a bigger example where we construct a binary search tree for the given list of numbers. So I have considered this list of numbers, and we will try understanding how we can construct a binary search tree for this with the help of insertion operation. So first I'm starting with the first element, which is 10. So we will write insert 10. Okay. So for inserting 10, I have already told you that if the binary search tree is empty, I can make our new value as root node. I don't have to make any comparisons now. I can directly make 10 as my root node. So I have made 10 as root node. So this is the present root node in the binary search tree. So now we will try and insert 15. Okay. So to insert 15, so we see that binary search tree is having a node. So I cannot make 15 as root node. So what can I do? I have to start making comparisons from now, right? So the present root node is 10. So I have to make comparisons between 10 and 15. So we know that 15 is greater than 10. So where should it go? So 15 has to be inserted as right child of 10. And what is the right child of 10? It is null. So since right child of 10 is null, I can replace this null position with 15. So I have to replace this null position with 15. And we have inserted 15 successfully. Now we will try inserting 11. So insert 11. So to insert 11, the comparisons has to be made right from the root node, and we compare 11 with 10. So we know that 11 is bigger than 10. So what we do? We check the right child of 10. So what is the right child of 10? It is 15. So now we make comparisons between 11 and 15. So we know that 11 is smaller than 15. So what we do? We insert this 11 as left child of 15. Why did I insert here? Because the 15 has a null left child. If 15 is having some different value instead of null, then I have to make one more comparison. So hope you understood these steps. Now, where will 6 go? We will see where 6 can be inserted now. Insert 6. So to insert 6 again, the comparisons has to be made right from the root node. So we will compare 6 with 10. So we know that 6 is smaller than 10. So where should this go? It has to go to the left child of 10. So what is the left child of 10? It is null. So the left child of 10 is null. Since 10 is having null left child, I can replace that null value with 6. And we have inserted 6 successfully. Now we will see how we can insert 9. Insert 9. Okay. Now again the comparisons has to be made from the root node. 9 is compared with 10. So we know that 9 is smaller than 10. So where should 9 be inserted? In the left side. And 10 is having left child called 6. So again we have to make one more comparison, 9 and 6. So we know that 9 is bigger than 6. So where should this be inserted? To the right side of 6. So right side of 6 is null. So since right side of 6 is null, I can insert 9 at this particular position. Okay. Now we will see where 2 goes. So to insert 2, we will again make comparisons because binary search tree is not null. Okay. So the comparisons will start from the root node. So 2 is smaller than 10. So again, I have to make comparison with left child of 10. So which is 6. So again, 2 is smaller than 6. Where should this go? The left side of 6. What is the left side of 6? Null. Since left side of 6 is null, I can replace this null position with 2. So I can replace this null position with 2. Now we will see how to insert 45. So to insert 45, again we have to make comparisons. So right from the root node. So we'll compare 45 with 10. So we know that 45 is bigger than 10. So it has to be inserted as right child of 10. So what is the right child of 10? So right child of 10 is 15. So make comparisons with 15. So 45 is bigger than 15. So where should this be inserted? To the right child of 15. What is the right child of 15? It is null. So since it is null, I can replace that null position with 45. Now we will insert 50. So inserting 50. Okay. So again, it has to be started from the root node. So we'll compare 50 with 10. So we know that 50 is bigger than 10. It has to be inserted in the right side, but 10 is having right child, which is 15. So I cannot insert it. What should I do? Make comparison again. So 50 is bigger than 15 again. So it has to be inserted as right child, but 15 is having a right child, which is 45. So what should I do? Make one more comparison. So 50 is compared with 45. So this time the 45 is having a null right child. So I can replace this null position with our new element 50. Okay. Now we will see how we can insert the last element in this example, which is 3. So we are inserting 3. Okay. So to insert 3 again, so first we have to make comparison from root node. So we will compare 3 and 10. So we know that 3 is smaller than 10. So where should this be inserted? To the left side of 10, which is 6. Again make comparison. 3 is smaller than 6 again. So it should be inserted as left child. But 6 is having a left child called 2. So again we make comparison. So which is 3 less than 2. I'm sorry. 3 greater than 2. So where 3 is greater than 2, so it has to go to the right side of 2. And what is the right child of 2? It is null. So since we got null, I can replace that null position here with the new element 3. So this is how the binary search tree can be constructed. Now let me take one more value to make you all understand when this binary search tree would go invalid. So if I ask you to insert a element called 6, so you'll see what actually happens. Okay. So here, so to insert 6, so what should we do? Make comparisons. So we make comparison between 6 and 10. We know that 6 is smaller than 10. So we have to check the left child of 10, which is 6. But here if you see, 6 is equal to 6. So since 6 is already in the binary search tree, so we cannot insert a duplicate element into binary search tree. If we insert this 6 in this position, what would happen? It will end up a invalid binary search tree. I have already made a video on properties of binary search tree and the time and space complexities of binary search tree. You can watch that video and you will be notified with the video too. And you can understand what I exactly mean. Okay, so we cannot insert duplicate nodes into binary search tree. In this case, we will notify the user saying duplicate node. So the user will understand we cannot insert a duplicate node into the binary search tree. Hope you have understood how the insertion operation works in binary search tree and how we can construct a binary search tree for the given list of numbers. And the steps are very simple and it is very straightforward. Hope you have understood this example. Now we will get into the search operation in binary search tree. Right? Before we get into the example, let us see the different steps we must follow in search operation in binary search tree. So the search operation is actually used to find a value in the existing binary search tree. So if the value is already in the binary search tree, it will tell us that the value is found. And if the value is not in the binary search tree, it will just tell us the value is not found. And there are certain steps to be followed for performing search operation. And we will see what those steps are. Okay. So the steps are very simple here. So first we will start making comparisons similar to insertion operation from the root node. Okay, so if the search value is found in the root node, so if the value present in root node, then we will simply return the root node as value found. What if the value is not found in the root node? Then we should either go to left subtree or either we should go to the right subtree. So we will go to the right subtree when the value is greater than the root node. And what we do there, we repeat the steps recursively for nodes in right subtree. And in case if the value is smaller, then we will search for the value recursively in left subtree. It is similar to the insertion operation. Okay. What happens if the value is not found after searching, after reaching the leaf node? So say you have reached the leaf node and still the value is not found. In that case, we will return to the user saying the value is not found. So this is how search operation steps actually work. We will start comparing right from the root node and we will reach till the leaf node if the value is not found. If the value is found anywhere in the comparisons, then we will immediately stop search operation and we will highlight that to the user saying the element is found in the binary search tree. Now let us see this with an example. Let me take this example to understand. Okay, so here I have taken list of numbers to search and you can expect similar kind of question in your exam too. So they will give you a binary search tree and this is the present binary search tree and they'll give you some list of numbers and they will ask you to perform search operation. So first we will do search operation for the first element which is 19. So which is searching 19. So to search 19, we have to make comparison right from the root node. So what is the root node? 19. So we make comparison. So here 19 is equal to 19. Since it is equal, we can directly inform the user saying value is found. And we will stop search operation here. Next, we will try and search the next element which is 30. To search 30, again the comparisons has to be started from the root node. What is root node value? 19. So we compare 30 with 19 and we know that 30 is bigger than 19. So what we do? We will check the right subtree of 19. So what is the right child of 19? 20. So we make comparison with 20 again now. So we compare 30 with 20. We know that 30 is bigger than 20. So what we do? We check the right child of 20 now. What is the right child of 20? It is 30. So now 30 is equal to 30. Since it is equal to 30, now we can tell that value is found. See, it is very simple, right? So now we will try searching the next element, which is 10. So to search 10, so these are all the steps that we follow. Search 10. Again, the comparisons are made from the root node. So we will compare 10 with the present root node, which is 19. So we know that 10 is smaller than 19. So what we do, we search in the left child or left subtree of 19. So left child of 19 is what? 10. So we compare 10 with 10. So since 10 is equal to 10, what we do, we tell the user that value is found. Okay. Now we will search the next element. We will try and search 20. So we are searching for 20. Okay. So again, the comparisons are made from the root node with 20 and 19. So we will compare 20 and 19. 20 is bigger than 19. So what we do, we check the right child of 19. What is the right child of 19? 20. So here we make comparison again. 20 is equal to 20. So what we do, we just highlight the user saying the value is found. The value is found. We will now search for 100. Searching 100. So here 100 is searched. So what we do? So we make comparison right from the root node. So 100 and 19 are compared. Since 100 is bigger than 19, we have to search in the right child of 19. What is the right child of 19? 20. Again make one more comparison. 100 is greater than 20 again. We have to check in the right child of 20, which is 30. And again make one more comparison. 100 and 30 are compared. Now we will compare this and we know that 100 is bigger than 30. Now we should check the right child of 30. What is the right child of 30? It is null. That means we have reached the leaf node. Since we have reached leaf node and the value is still not found, now we can tell the user that the value is not found. Now how can we search 15? So this is how we search for 15. Okay, to search 15, the comparisons are made from the root node again. So we will compare 15 with 19. So we know that 15 is smaller than 19. What we do? We go to the left child of 19. What is the left child of 19? 10. So we compare 15 with 10. So if you compare 15 with 10, it is bigger than 10. So what we do? We check the right child of 10. What is the right child of 10? It is 15. Now 15 is equal to 15 if you make comparison, and now we can say that the value is found. So this is how the searching operation works in binary search tree. Hope you have understood the insert operation and search operation in binary search tree, and how we can construct a binary search tree for the given list of numbers, and how we can perform search operation for the given list of numbers in the existing binary search tree. If you have any doubts in this present content or in the topic, please feel free to mention that in the comment section. And if you want me to make a dedicated video on any specific topic, also mention that in the comment section. If you like the content of this video, please do like this video so that this video can be recommended for many users and for many students, and they might also watch this video. And if you feel that this video is worth of sharing with your friends to learn,